So let's just quickly touch base. What was the point of Green's theorem? Did it feel disconnected? Say it again. Conservative field too, in addition to Green's theorem. Why did you learn them at all?
Well, was it for like closed system? Or...
That was the reason when you could use it, but why teach it at all? Why not just do direct method for everything? Direct method works for everything. It's a shortcut. So Green's is a shortcut, and Green's doesn't require it to be conservative, but it does require orientation of the curve to be counterclockwise. It did require, so it has some assumptions under it that you have to have this closed curve, so you can't just have a path. So we're really going to be talking about closed curves here. Green's theorem is a special case of Stokes' theorem. It is when the curve is on the floor. And in fact, some people talked about curl in their classes for Green's theorem because that's the two-dimensional version that they were using. But here's a stock example. I'm going to go through the direct method and what's changed here and the direct method, kind of just overview, because we just won't have time to get to the actual Stokes and a parameterization and so forth. So in this example, I'm given a vector field. And I made it super easy. This is my stock example. I put vector thingamajigs on here. And I'm giving a curve. You're still given a curve. The curve now is off the ground and it's up in the air. And I tried to make things easy on myself with the computations, as I did with the example that I would like you guys to try. I put a triangle, but up in the air. So this point here is 1, 0, 0. This point here is 0, 1, 0. And this point here is 0, 0, 1. This is my start point. I'm going over here to this point, one line segment. I'm going to call that C1 for curve 1. And then I'm going to go over here for the second line segment. I'm going to call that C2. And then I'm going to go over here for the third line segment. I'm going to call that C3. So then, since the curve is up in the air, I have to parameterize that curve. And the only way you can do that is to parameterize each line segment separately. The formula is the same, exactly the same. You need to find this, once you find this guy, you find its derivative, you dot product the two, and you have an integral, you need the start and the end. All of that's the same. The work just got a little messier. That's all. I made it sound like it's nothing. You with me? For this particular loop, it's a triangle, it's broke up into the 3 pieces, and you do the integrals separately for each piece. So I'm going to do work for C1. This is the work for C1 only. So I have start was 1, 0, 0, and the end point for C1 was 0, 1, 0. The formula for a parameterization of a line segment is still the same. So that hasn't changed. So your formula looks like this. It's P0, the initial starting point, plus T times a direction vector. How do you find the direction vector? How do I find this V? This is the parameterization. How do I find this formula for V? Yes, tail to head. So I take the end point and subtract the beginning point. So 0 minus 1 gives me minus 1. 1 minus 0 gives you 1. And 0 minus 0 is 0. That's called a direction vector. It's the vector that points in the direction, this direction, there to there. And so I get from this, if I map it all out, I get from this, my R of T looks like 1, 0, 0 plus T times negative 1, 1, 0. And then I put that all together into its components, and you get R of T is equal to 1 plus T minus T, T, and 0. So my X is 1 plus T, my Y is T, and my Z is 0. Only thing new here is that you have Z equals 0, a Z component now. The work is exactly the same as the direct method, which I suspect a lot of you got correct on the exam.
Why wouldn't X be 1 minus T?
Did I do it wrong?
Yes,
you did.
Okay.
I make minus sign errors. The answer is I make minus sign errors. Okay, and I also need this start and end point. Since Y is T, and the Y here starts at 0 and the Y ends at 1, so I'm just using this. This is my Y's here. I just look at the Y component. Y starts at 0 and ends at 1. So T starts at 0 and T ends at 1. It was set up for me. Of course, in the grand spirit of teachers, I gave you something in your example that's not set up. You get something like T equals 2y, something like that. So you have to divide, you have to solve for y by dividing. Do you remember the steps, or is it already out of your brain? You need now in the formula that f of r of t. How do you get that? Let's see what you remember. My f was x, y, z. My x was 1 minus t. My y was t. And my z was 0. That's how you did it. Does this sound familiar? Oh, yeah. Do I need to put Sophia for a leadership challenge and move you next to her?
Me?
Yeah.
No.
Why? Yeah, I'm confused. Is he not getting
No.
I think Ryan's
So I know it's Ryan's fault.
me.
I think Ryan just got to move to a different location.
Yeah.
What's crazy is like I'm like so quiet right now.
It's like distracting anybody. We'll figure
So where do we move Ryan?
Back here. Yeah. And it's
If I move him back there, you're gonna be responsible for him.
That's okay. I'm trying to find a responsible.
I think we should have like a chair in the front for Ryan.
Wait, I would find him for Ryan. I'm being serious.
So Ryan faces everybody out that way.
No, we love you, Ryan.
At least you guys made me laugh. Like, when I look at the material, I'm laughing. Yeah. Okay, so F dot. Okay, I need R prime of T too. Where does that come from? How do I get the R prime of what? Some people took the derivative of this on the test. Not this class. I go back to the top. So I get this is minus 1, 1, 0. And then somebody asked me last class about this being the same as a direction vector. It's because it's this kind of like the slope. But it's not always going to be like that. It's just because it's a line segment. And now I dot product these two guys with each other. And I calculate the integral. So I made this super easy for myself. I got this thing, and I'm not going to actually calculate the integral. It's actually super easy. Dot these two, so I get minus 1 plus t plus 0 dt. And that turns out to be the integral from 0 to 1 of minus 1 plus 2t dt. And everybody can do this. Well, you say that's not so bad, but just remember, I've only done C1. Now I got to do C2 and C3. So even for this simple example, it's a pain. It's a lot of busy work. Go ahead.
What?
Do you have a question?
No, I don't see the point
Of what?
of all of this.
It's just this hard, like how to
It's
compute
just
it.
they just want to make life harder.
It's not they. It's the people, like this is the math that underlies partial differential equations. And that's why it's being used. But we're kind of not told that as a student. And so I got into grad school thinking I wanted to do partial differential equations. My thesis is on partial differential equations. I stuck it through the end. I complained every second. You know me now. I complained all the way through. But that's what this is. It's like Calc 3 was really important. It was like, I was watching cartoons during Calc 3, so I had a lot of trouble. But I learned my Calc 3 in partial differential equations because it was needed. And even the why we do Stokes' theorem and everything, that was there that I learned it. But that's what the math is for. It's for the next step in differential equations. Okay. Why don't I have you try out the middle one on the direct method for yourself? Just take it all the way to the integral. Though I don't really care about the final integral. Work that middle one through. Otherwise, you'll be just sitting here and listening to me.